In this video, we're going to focus on finding the empirical formula from mass, percent composition, and also we're going to work on some combustion analysis problems, finding the empirical formula from the mass of CO2 and H2O produced in a reaction. But let's begin. So what exactly is the empirical formula? So let's say if you have the formula C3H9O6. So given the molecular formula, how can you find the empirical formula? The empirical formula is the one that has the lowest ratio of subscripts. So notice that we can simplify the numbers 3, 9, and 6. Each of these numbers are divisible by 3. So the empirical formula of C3H9O6 is C1H3O2, or simply CH3O2. So here's another example. Let's say if you wanted to find the empirical formula of C4H8O16. What's the answer? Since each number is divisible by 4, it's going to be C1H2O4. So as you can see, the empirical formula is simply the formula that contains the lowest whole number ratios. But now let's work on an example problem. So let's say if you have a compound and you're given the mass in grams of every element in this compound. How can you use that information to determine the empirical formula? The first thing that you need to do is convert the grams of every element into moles. So let's start with 20 grams of carbon. Now the atomic mass of carbon based on the periodic table is 12, which is also known as the molar mass. So 1 mole of carbon is equal to 12 grams of carbon. Now you want to write it in such a way that the units grams of carbon cancel. So 20 divided by 12 is about 1.67 moles of carbon atoms. Now let's convert grams of hydrogen into moles. So we have 3.33 grams of hydrogen. The molar mass of hydrogen is about 1. So we're just going to round it to 1. So these units will cancel. And it's going to be 3.33 moles of hydrogen. Now let's do the same for oxygen. We have 26.67 grams of oxygen, and the molar mass for atomic oxygen is 16 grams per mole. .67 divided by 16 is about 1.67 moles of oxygen. Now what do you think we need to do next? What is our next step? At this point, once you have the moles of every element, divide each number by the lowest number that you see, in this case 1.67. And if possible, round it to the nearest whole number. 1.67 divided by 1.67 is 1. 3.33 divided by 1.67, that's about 2. And the last one is 1. So notice the numbers that we have. 1, 2, 1. So the number associated with carbon is 1. So I'm going to write C1. The number that is associated with hydrogen is 2. So that's H2. And for oxygen we have 1. So C1H2O1. That is the empirical formula. Now, how can we use the empirical formula to find the molecular formula? Let's say if this question gave us some extra information. Let's say it stated that the molar mass of the molecular formula is 180 grams per mole. How can we find the formula, or the molecular formula, given the molar mass of the molecular formula? How can we do that? Now, what we need to do is calculate the molar mass of the empirical formula. Carbon has a molar mass of 12. For hydrogen, it's 1, but there's 2 of them. And for oxygen, it's 16. 12 plus 2 is 14, plus 16, that's 30. Now, let's think about this. The molar mass for the empirical formula is 30 grams per mole. The molar mass for the molecular formula is 180. So what do you think the subscripts are for the molecular formula? If we divide 180 by 30, this will give you 6. You can cancel the zeros. 18 divided by 3 is 6. That means that we need to multiply the subscripts by 6. So if you take C1H2O1, multiply the subscripts by 6, it's going to be C6H12O6. So as you can see, the molecular formula has the same ratio as the empirical formula. 612,6 is in the same ratio as 121, but the molar mass of the molecular formula is 180. You can check it, you can calculate it. If you type in 6 times 12 plus the 12 hydrogens plus 6 times 16 for oxygen, this should give you 180. Let's try another problem. So we have a compound that contains 81.8% biomass carbon and 18.2% of hydrogen. So we have the percent composition. How can we use that information to find the empirical formula? So if you're given the percent composition, since it's based on mass, you can simply convert it to grams. Now think about it. If the compound is 81.8% biomass of carbon, that means that there's 81.8 grams of carbon per 100 grams of compound, because 81.8 divided by 100 is 81.8%. And if it's 18.2% biomass of hydrogen, that means that there's 18.2 grams of hydrogen per 100 grams of compound. So we have 81.8 grams of carbon and 18.2 grams of hydrogen, which means that we have 100 grams of the compound in total. And that's why we can simply convert the mass percent into grams. Because if you do that, it's based out of 100, and 81.8 out of 100 is 81.8%. So it works. It's the ratio that's important. Now what we're going to do is convert the grams of every element into moles, just like we did before. So let's start with carbon. So we know the molar mass of carbon is 12 grams per mole. .8 divided by 12, that's about 6.817 moles of carbon. Now we have 18.2 grams of hydrogen, and the molar mass, we're just going to round it to 1. You can use the exact number if you want. You should still get the same answer. So we have 18.2 moles of hydrogen. So once you have the moles of every element, divide each number by the lowest number. So let's divide each number by 6.817. So this is going to give us a value of 1. And for the other one, 18.2 divided by 6.817, that's equal to 2.67. So what would you do in this particular case? Because notice that we don't have a whole number here. It's 2.67. And you don't want to round it to 3, especially after you divide it by the lowest number. So what would you do in a situation like this? What should we do? What I would do is I would write the formula. So notice that the 1 is associated with carbon and the 2.67 is associated with hydrogen. So we have the formula C1H2.67, but we just have to modify it. Now we need to multiply the subscripts by a whole number that will convert the 2.67 into a whole number. Now how can we do that? Now if you're familiar with fractions, you know that 1/3 is 0.33333 repeated. 2/3 is 0.66666 repeated, or if you round it, 0.67. If you see the numbers 0.33 or 0.67, it's a good indication that you need to multiply it by 3. If you do that, you can get rid of the fraction, giving you a whole number. Now here are some other examples. If you get a decimal that is 0.2, multiply it by 5. Because 1/5 is 0.2. This will turn into a whole number. If you see 0.25, multiply it by 4, since 1/4 is 0.25. If you see, let's say, 0.5, multiply it by 2, because 1/2 is 0.5. So hopefully you see a pattern. If you see 0.167, multiply it by 6, because 1/6 is 0.167. So let's see what happens if we multiply the subscripts by 3. So 1 times 3 is 3. And what is 2.67 times 3? This will give you 8.01, which we could say is 8. If you have 2.666666 repeating times 3, it's going to be very, very close to 8. So this is the empirical formula with the lowest whole number ratio. So this is the answer. Now that we have the empirical formula, let us find the molecular formula. So first, find the molar mass of the empirical formula. So it's 3 times 12 plus the 8 hydrogens. So the molar mass is 44. Now the molar mass for the molecular formula is 88. If we divide 88 by 44, we're going to get 2. So to find the molecular formula, we need to multiply the subscripts by 2. And if we do that, we'll get the molecular formula, which is C6H16. So here's the molecular formula, and here is the empirical formula, which has the lowest whole number ratios. So that's it for this problem. Now, we have a combustion analysis problem, and our goal is to find the empirical formula of the compound. We have the mass of the compound, it's 3.48 grams, and we know that the compound contains only carbon and hydrogen. Now, in a combustion reaction, let's call this compound CXHY, because we currently don't know the subscripts, but we know the elements in the compound. This compound is going to react with oxygen to produce carbon dioxide and water. Now we can't balance the reaction since we don't have the subscripts for C and H in the compound. So all we can do is find the number of moles of carbon and hydrogen that is produced in this reaction, or that is found in CO2 and water. The number of moles in CO2 and water is equal to the number of moles of carbon and hydrogen in the compound, since the carbon atoms in CO2 and the hydrogen atoms in water came only from this compound. So once we have the moles of carbon and the moles of hydrogen, we can find the empirical formula, and that's what we need to do. So let's start with the grams of CO2. So if we have 10.63 grams of carbon dioxide molecules, how many moles of carbon atoms do we have? So first, we need to find the molar mass of CO2. The atomic mass for carbon is 12, and for oxygen is 16, but there's 2 of them, so we're going to multiply by 2. 2 times 16 is 32 plus 12, that's 44. So there's 44 grams of CO2 per 1 mole of CO2. Now we need to convert to moles of carbon. Notice that for every molecule of CO2, there's one carbon atom. So we can say 1 mole of carbon is equal to 1 mole of CO2. It's a 1-to-1 ratio. So now moles of CO2 cancels, and we could find the moles of carbon. So it's only going to be 10.63 divided by 44. And you should get 0.2416 moles of carbon. Now let's do the same thing with water. Let's start with 5.22 grams of H2O, and let's convert it to moles. The molar mass for water is 2 for hydrogen, is 2 hydrogen atoms plus 16, so it's 18 grams per 1 mole of H2O. Now, how can we convert from moles of water to moles of hydrogen? So in the formula of H2O, there's 2 hydrogen atoms per molecule of H2O. So we could say that 1 mole of water contains 2 moles of hydrogen. It's a 1-to-2 ratio. So to get the answer, it's going to be 5.22 divided by 18 times 2. And so we have 0.58 moles of hydrogen. So now let's divide by the smaller of the two numbers. So that's going to be 0.2416. So the number associated with carbon is 1, and 0.58 divided by 0.2416 will give us the number associated with hydrogen, which is 2.4. So let's make some space. So we have the formula C1H2.4. So we have a decimal. What number should we multiply the subscripts by to convert the 2.4 into a whole number? Is it 1? Is it 2? Is it 9? Is it 20? What number do we need? Now remember, earlier in this video, we said that if you see 0.2, multiply by 5, because 0.2 is 1 over 5. Now I'm going to add, if you see any multiples of 0.2, multiply by 5. So multiples of 0.2 are 0.4, 0.6, 0.8, and so forth. So if you see 3.6, multiply by 5, because that's going to give you a whole number. 3.6 times 5 is 18. If you see 4.8, 0.8 is a multiple of 0.2 multiplied by 5. Now let's say if you don't remember all this stuff. What can you do to figure out the answer? Is there a systematic way of getting the answer? And there is. You know 1 is not going to work, so start with 2. Multiply by every integer and increase in order, and eventually you'll get the answer. If you multiply by 2, it's 4.8. That doesn't work, so let's move on to 3. If you multiply by 3, that's 7.2. That doesn't work. If you multiply by 4, that's 9.6. That doesn't work. If you times it by 5, well, that's going to be 12. Let me double check that. And it is. So if you're not sure, just start with 2 and just multiply it by every number after 2. And eventually you'll find it. So then it's going to be C5H12. So that is the empirical formula for this compound. Now, let's say if the molecular formula has a molar mass of 216. What is the molecular formula in that case? Feel free to pause the video and work on that example. Go ahead and figure out what the molecular formula is. First, let's find the molar mass of the empirical formula. So the atomic mass of carbon is 12, and for hydrogen it's 1, but times 12. So it's 60 plus 12, which is 72. Next, take the molar mass of the molecular formula and divide it by the molar mass of the empirical formula. So 216 divided by 72 is 3. 21 divided by 7 is 3, and 6 divided by 2 is 3, so the whole thing is 3. So now we got to multiply the subscripts by 3. So the molecular formula is going to be C15H36. So here is the last problem of the day. It's another combustion analysis problem. But in this problem, the compound contains 3 elements instead of 2. It contains carbon, hydrogen, and oxygen. We have the mass of CO2 and water produced just like the other problem. But how can we determine the empirical formula of the compound? Feel free to pause the video and work through this example. And then once you have the answer, unpause it to see if you have the solution. Now, what do you think the first thing that we need to do in this problem? Now, there's something important that you need to realize. If we write a reaction, we know the compound contains carbon, hydrogen, and oxygen, but we don't know what the subscripts are. In a combustion reaction, it's going to react with O2, and it's going to produce CO2 and water. Now, here's what you need to know. The moles of carbon atoms produced, or the moles of carbon that is found in CO2, and the moles of hydrogen that is found in H2O is equal to the moles of carbon and hydrogen found in this compound. However, the moles of oxygen that are found in CO2 and water does not equal the moles of oxygen in this compound, because some of the oxygen in the air incorporates itself into CO2 and water. So you don't want to find the moles of oxygen from CO2 and water. You need to find it a different way. So here's what we need to do. The first thing we need to do is find the moles of carbon and hydrogen, just like we did before. And then we're going to convert the moles of C and H into grams. Once we have the grams of carbon and hydrogen, we can calculate the grams of oxygen. For example, let's say if there's 10 grams of the unknown compound, and 4 grams is from carbon, and 1 gram is from hydrogen. So that means the missing 5 grams must be oxygen in this compound, because the masses of carbon, hydrogen, and oxygen has to add up to the mass of the compound. And that's the best way in which you want to find the mass of oxygen. Once you have the grams of oxygen, you can convert it to moles. And once you have the moles of all 3 elements, you can find the empirical formula. So that's what we want to do for this problem. So let's start with the 8.952 grams of CO2. Let's convert it to moles. So we know the molar mass of CO2 is 44 grams per mole. So these units cancel. And we know that there's 1 carbon atom in a single molecule of CO2. So the molar ratio is 1 to 1. .952 divided by 44 will give us 0.2035 moles of carbon atoms. So feel free to write that number down, because we're going to need that later. Now let's do the same thing for water. We have 2.354 grams of H2O. And we know the molar mass of water is about 18 grams per 1 mole. The molar ratio for water is 2 to 1. There's 2 moles of hydrogen atoms per 1 mole of H2O. So now let's do the math. It's 2.354 divided by 18 times 2. And you should get 0.2616 moles of hydrogen atoms. So now at this point, we need to convert the moles of carbon and the moles of hydrogen into grams. Once we have the grams of carbon and hydrogen, we can subtract it from the mass of the compound to get the grams of oxygen. You don't want to try to get the moles of oxygen from CO2 and water. Remember, the oxygen that's in the air, some of it went into CO2 and water, so you don't want to get the moles of O2 or the moles of O from that method. So let's start with the 0.2035 moles of carbon atoms. And let's convert it to grams. So the molar mass of carbon is 12. .2035 times 12 is about 2.442 grams of carbon. Now let's do the same thing for hydrogen. So let's start with 0.2616 moles of hydrogen, and let's convert it to grams. So the molar mass of hydrogen is simply 1. It's 1 gram per mole. So this number won't change. So we have 0.2616 grams of hydrogen. Now that we have the mass of carbon and hydrogen, we can find the mass of oxygen. So the mass of oxygen is going to be equal to the mass of the compound minus the mass of carbon minus the mass of hydrogen. So the mass of the compound is 4.563 grams. For carbon, it's 2.442, and the mass of hydrogen is 0.2616. So you should get 1.8594 grams of oxygen. Now let's convert grams of oxygen into moles. So the molar mass for atomic oxygen is 16 grams. So 1.8594 divided by 16 is about 0.1162 moles of oxygen. Now earlier we mentioned that we had 0.2035 moles of carbon, and we also had 0.2616 moles of hydrogen. So now we're going to divide each number by the smaller of the three numbers, which is going to be 0.1162. So for oxygen, it's going to be 1. For carbon, you should get about 1.75. And for hydrogen, you should get 2.25. So the formula should be C 1.75 H 2.25O1. Now what number should we multiply the subscripts by so that we can get whole number ratios? Let's start with 1.75. What number can we multiply by? So if you go in order, 1.75 times 2 is 3.5. Times 3, that's 5.25. Times 4, that's 7. That could work. Now let's check 2.25, because this must also work as well if we're going to use 7. 2.25 times 4 is 9. So 4 is our number. Now, if you remember, anytime you see 0.25, you want to use 4 because 1 over 4 is 0.25. And 0.75 is a multiple of 0.25. 3/4 is 0.75. So if you see 0.25, 0.5, well, 0.5 you could just multiply by 2. But if you see 0.25, 0.75, or any multiple of 0.25, you can multiply by 4. Or you could just multiply by every number after 2 until you find the number that works. So if we multiply everything by 4, it's going to be C7 H9 O4. This is the empirical formula of the compound. So that is it for this video. Thanks for watching and have a good day.